Okay, last one. Um, Thank you for bearing with me. I hope this is more helpful than it is tedious. But again, we could rush through these quite a bit faster, but since you guys haven't had any of the in-class discussion stuff, I thought it might be good to try to impart as much perspective as I could for this opportunity here. This problem really is with the box, really is one of the classic problems for this stage and this material. It's a problem that you'll see over and over again. Those of you who go into calculus, it's used in calculus. You probably saw it in Math 95. People just love this example, and I'm one of those people. Um, for a lot of these problems, the fence problems in your textbook, make sure you're looking at those. And these rectangular piece problems, even the truck problem we're going to do next, they're really metaphors for other things. I mean, there are people who make boxes like this. I had a student once who made boxes for toolbox drawers. And what he did all day was put the pieces in a machine that folded this up. And when we learned this, he was kind of upset because the guy who used to come by once or twice a week and fiddle with the knobs to change the size of the drawers made so much more money than he did because that guy knew how to do this and he didn't. And he was shocked that that was all it was, is the tools that we will use for this. But a lot of these types of problems are about restricted resources. How do we maximize volume out of this? How do we, particularly for the fence problems, what's the relationship between restricted resources, be that time, be it steel, um, be it payroll, be it work hours, be it whatever the restricted resource you happen to be working with is. These are all really metaphors for that. So if you're getting a little frustrated with, I don't build fences and I don't work with steel, try to think of them in terms of that limited resource that you may be working with. But that being said, you've got this piece of steel that is 30 inches by 24 inches, and they're going to cut squares out of the corners. So that's going to be cut away. That's going to be cut away. It's going to be a square, sorry. That's going to be cut away, all the same size, and that's going to be cut away. And that's going to allow you to fold it along these lines, fold up those resulting tabs, and you're going to get a nice little box. So that box is going to be so high, and that tab's going to fold up. It's going to be a given length. It's going to be a given width. Oops, sorry. But the top's going to be open because we're folding up those tabs, but we're not making a top for it. And that's why the guy did it for toolbox pieces. But anyway, so if we want to build an equation for this, we have to remember how to find the volume of a rectangular solid. So the volume of a rectangular solid, a box, is length times width times height. So we have to figure out an expression for length, width, and height. So this height there, that's what we're cutting off. That's the side lengths of each of these squares. So that's what we want our variable to be, and we're even told in terms of the common side length of the squares cut from each corner. So we want to give that our variable. We can go ahead and call it anything we want. We're going to call it x. So all of these squares are x by x, x by x, x by x squares. So that's what we're cutting off. So that height is going to be x. So our volume, we can let the height be first, is x. Now we need our length and our width. Well, this length all the way across was 30. But we've taken two chunks out of it to make this length. We've taken that 30 and removed 1x, 2 x's. So this length is now 30 minus 2x. So 30 minus 2x. Now this width here, the same way, that width was 24 from end to end, but we've taken out 2 of the chunks. So we've got 24 minus 2 x's. So 24 minus 2 x's. So that's an equation. You plug in x and you will have a nice model for how much volume there is in that box. It's nice just to note that it does have some domain restrictions. We certainly can't pick out anything that's negative. We can't cut out negative sized squares. We also can't cut anything more than 24 inches. At 24 inches, you're going to get 0 here, because 24 minus 2 times 24. If you cut 12 inches from this side and 12 inches from that side, you're not going to have any width left. So there's some interesting things with this function. We will play with it later when we start talking about trying to maximize higher degree polynomials. You multiply all this out, and you're welcome to. But you multiply all this out, you get a third degree polynomial. Well, we know how to find the maximum of a quadratic second degree polynomial, but we don't really have a tool right now for third degree. So this is a tool we're going to keep playing with. You might want to check the graph out. It's kind of nice. Graph comes up, down, and back up. At 0, this volume will be 0. The flat sheet of steel doesn't have any volume. This here happens exactly at the 12, because when you cut off 12, it's flat again. Now the model keeps going. This point happens, by the way, at 15. This is also 0 at 15. And the model does keep going, but none of this can happen. The actual domain, the only part of the problem we care about, is this 0 to 12, because that's all you can actually do and still get a real box. But all that's beside the point. Your question was, write an equation for the volume of the box in terms of the common side length of the square cut from each corner. That's your answer. I know. Okay. Last one, 15. By the way, be sure to look at the fence problems. I've mentioned them 2 or 3 times. Go to your book, find the fence problems, practice them. We like fence problems. Fence problems are good. There's a hint and a half there. Okay, so you got a freeway. You got a truck that's entered this freeway. And that truck is going, how fast is the truck going? Where'd my problem go? 55 miles per hour. This is like that problem you hear in nightmares about the trains going in both directions, isn't it? And it's been doing this for 10 minutes. So this time is 10 minutes. Notice it's a time, it's not a distance. It might be nice to know that in terms of distance, so we know where it is. But if you're going 55 miles an hour for 10 minutes, we could figure out how far that is. That's 55 miles per hour, so 10 minutes is 1/6 of an hour. So 55 times 1/6 is whatever the heck 55 times 1/6 is. I'm just going to go, this implies we are 55/6 of a mile, or miles, down the road. So we've been driving for 10 minutes, so we're 55/6 of a mile down the road. And that might be an ugly number, but ugly numbers come up, so we got to be careful. At the moment, after those 10 minutes, at the moment where you're at 55/6 miles down the road, the speedy little car gets on. I don't know why the speedy little car has big wheels, it just does. And this speedy little car is going 70 miles an hour. By the way, I don't recommend driving 70 miles an hour, but it happens. And we want to know when this car is going to catch up and be at the same place as this truck at the same time. So we need a model for each, based on a model of position. Well, this truck's model, its rate of change, its slope, is 55. I'm going to use t for time. So it's 55 miles per hour, that's its rate of change, that's its slope, times your t, plus its initial value, its y-intercept, 55 sixths. Again, this really is mx plus b. If we call time equals 0 when this car gets on the freeway, the initial position of this truck is 55 sixths. And its rate of change, its slope, is 55. You're just given a line here. Heck, we could even graph it if we wanted to. The truck starts at 55 sixths at time equals 0. It did start way back here somewhere at 0, but this is the time it was waiting for the car, and it's going to continue to go on. Now the car starts at the on-ramp, but it's going a lot faster. So what we're trying to find is what this intersection point is. And of course, just in case you're curious, this is time, and this is distance from the on-ramp. So this is the equation for the truck, capital T for truck. The car is going 70 miles an hour, so 70 miles for every time, plus, where is it starting? Well, it's starting exactly at the on-ramp, so its initial value is 0. Now, some people like to do this problem, by the way, where this is 0 and this is negative 55 sixths, and you can do that as well. It just essentially moves this graph down a bit. I prefer this way, but it's up to you. And you're wanting to find when they meet up, so when t is equal to c. When is the truck in the same spot as the car? Well, it's going to happen when 55t plus 55 sixths, when that is equal to 70t. We just got to solve this model. So real quick, subtract the 55t, subtract the 55t, you'll get 55 sixths equals, was it 15t? Divide by 15, divide by 15, you get t equals, I'll write that as a multiplication so I don't give myself a headache. Let's see, 11 and 3, so it's 11/18. Okay, we get 11/18, but the question is, oops, sorry, you couldn't see any of that, could you? So set those equal to each other, subtracted the 55. To get the 55 sixths equals 15t, divide the 15 on both sides. Set it as a multiplication, because dividing by 15 hurt my head, so I multiplied it by 1/15 instead. Cross-canceled those to get the 11/18. The question is, 11/18 what? Well, in this problem, we're all in miles per hour. And notice we turned those 10 minutes into 1/6 of an hour. Our time in this problem is hours. So t, that's 11/18, 11/18 hours. If you want to turn that into minutes, you'd have to do a little unit conversion thing and turn that into minutes. And you're certainly welcome to do that. But just to get us done here, we could say it will take, again, it's a word problem, so answering a sentence, 11/18 hours for the two cars to meet. Now, changing that into minutes would probably be best, and if I put that on a test, I'd probably ask how many minutes after the car enters. So you might remind yourself how to do unit analysis there, but you're really going to multiply that by 60. 11/18 times 60 will give you minutes. Just clean that up. So that's all of them. If you have any questions, let me know. I know this was long. It was, what, an hour and change. But I hope that the extra time gave you some extra insights. And yeah, if you have any questions, let me know.